the opportunity to speak. So this is joint work with a number of people who are, well, until very recently have all been at University of Toronto, Andronowski, Joel Kamnitzer, Tanya Liebman, and Calder Morton Ferguson, who, with the exception of Joel, are now elsewhere all. So, okay, so we'll be, as I said, we'll be talking about heaps, crystals, and preprojective algebra modules, and realized that maybe the title should have been crystals, heaps, and preprojective algebra modules, because I want to start with talking about crystals first. So to motivate the discussion, so consider SLN, the Lie algebra of trace zero matrices, n by n matrices, and the vector space Cn with the action of SLN. Then we can pick the standard basis vectors. Maybe I should get my pointer out. How do I do that again? Here. Okay, right. So this is right. So the standard basis vectors form a basis of the vector space V that has several very nice properties, including that each of the standard basis vectors is a weight vector for the maximal torus, the diagonal matrices inside SLN, and these matrices with a single entry equal to 1 and 0 elsewhere that are off diagonal, these EIJ matrices, they almost permute the standard basis vectors. Namely, if I multiply EIJ to VJ, I get VI, and I get 0 otherwise if the J, well, if I multiply it to a different basis vector. And in fact, I don't even need all of these EIJs, I just need the EI plus 1 I's to be able to reach any basis vector from V1. So the way I want to think about this, the way I want to think about the, somehow visually thinking about this representation as a color-directed graph. For example, I could put my basis vectors as the vertices of my graph, and these specific matrices that correspond to these, that will be called lowering operators, as the arrows of my graph, and the color is, well, it's colored by the simple roots of this algebra. So so this is a very nice picture, and it makes us be able to understand this representation very well. And what we would like to do is to generalize this idea, and hopefully it should be compatible with the notions of, well, with the kind of operations you like to do in representation theory. So taking tensor products or doing branching. So this works not so great as soon as you consider other representations. So for example, if you have consider the adjoint representation of SL3, the problem here is that now so I'm using the same notation, the EIJ for the particular matrices in SL3, and the high weight vector in this case is the matrix E13, and it kind of works for a while, but then I'm sort of running into trouble when I want to choose a basis for the Cartan, that is the zero weight space of this representation, where I need to pick two vectors that should span H, but I have 4 distinguished subspaces, the kernel of the F1 going out, and the kernel of F2 going out, and the image of F1 coming in, and the image of F2 coming in, and they're actually 4 different subspaces. So I'm not going to be able to choose 2 of them to be compatible with this color-directed graph structure. So, but there is hope here, so we don't have to give up. We just have to get a little more complicated. So this construction is due to Kashiwara and I guess also Lustig, that there's a way to fix this problem by first moving by seemingly a more complicated thing, the quantized, the quantum group, the quantized universal enveloping algebra UQ of G, and then we can take some sort of a limit as Q goes to 0, and in this setting, we can always choose this basis that we'll be calling a good basis that results in in an object which is a color-directed graph where the vertices are the basis elements and the edges are labeled by the lowering operators. And this is what we'll call a crystal. And because of the representation theory of UQ of G as being very similar to that of U of G, this lets us study U of G representations combinatorially. So why do we like crystals as opposed to just working with the representations is because the rules for tensoring crystals and branching are now completely combinatorial. So here's the actual rule for tensoring SL2 representations, which is I make, well, here I have two of the SL2 representations. One of them is C4 and the other one is C5, a 5-dimensional one. To tensor them, I just need to follow this pictorial rule that I start from this high weight vector here, and I go to the right, and then I turn down, and then I continue as long as I have room left for me. And this is in some sense, this is the only rule you need to remember to be able to reconstruct old representations. So this is, I like this a lot. So for example, it's a well-known theorem that the dimension of an irreducible SLN representation of high weight lambda is the number of semi-standard Young tableau with weight of shape lambda with entries up to n. And the crystal kind of makes this into a bit finer decomposition that I can actually use these Young tableau to model the crystal where the lowering operators act as turning, so the lowering operator F1 acts as turning an entry 1 into a 2, and the lowering operator F2 acts as turning a number 2 into a 3 in the tableau. All right, so the crystals is the objects we are going to try to study. And now we'll come to a definition. So if I have due to Stembridge, so if I have a Coxeter group, then I call an element W fully commutative if any reduced word for W can be obtained from any other by using only the commuting relations in the vowel group. So I'm not allowed to use the braid relations. So in general, as an example, if W is the symmetric group, then fully commutative is actually equivalent to being 3-to-1 avoiding in terms of the permutation. So to see maybe, so we'll be interested in a kind of special kind of fully commutative elements that are associated to minuscule representations. So fundamental weight is called minuscule if W acts transitively on the set of weights that appear in the representation. And if we consider, so if I have a fundamental weight omega p, then let p sub p be the maximal parabolic associated to that fundamental weight, then there is a unique minimal rank representative that I'll be calling W naught p for the longest element in the quotient, and that representative is fully commutative. So the example is that if we take G to be SL4, then all of the fundamental weights are minuscule, and I have this representation V of omega 2 being the second wedge power of C4, and in this case W naught P is this following element written as a reduced word, which we can see is fully commutative, right? The only thing you can do is switch the order of S1 and S3. There's no other relations that we could change, that we could use to change this word. Okay. Right. So given, so this is again following Stembridge's paper from '96. Given a word in W, we can define the heap of the word to be the following combinatorial object. It consists of a partially ordered set on as many entries as the number of simple reflections in the word, where I have this relation that I is going to be curly less than equal to J if I is actually greater than J and the corresponding entry of the Cartan matrix is not equal to 0. And we want to take a transitive closure of this relation. So, and I also have a labeling function that sends an element to the corresponding simple reflection. So
sorry,
yeah.
So it's a reduced word, right?
It doesn't actually need to be a reduced word, but we'll end up considering mostly reduced words.
So the poset on that you're defining on K could be not fixed, or?
So yeah, so the poset, this is the definition of my poset. So I think it's a lot easier to try to think of, maybe not in terms of this definition, but the more visual version of heaps, which is you kind of imagine that you have some runners arranged according to the Dinkin diagram, like here for A3, and you're dropping little beads onto these runners from the top in the order that's well, I'm dropping these last reflections first. And the balls are just large enough that if you drop something on a runner that already has bead on a neighboring runner, then it's sort of it's going to block it from falling all the way down to the ground. But if if the two runners are not adjacent, then this won't happen. So for example, in this here, we have the first and the third runner, and you see that the balls that we are dropping the beads are small enough that they could both simultaneously fall into onto the ground. But if I put something on the second runner, then that will block them. So this figure here is the heap of the element S2, S1, S3, S2. So you imagine that you're dropping these beads onto the runners in the order. I drop one on the second one, then one on the first one, then one on the third one, then one on the second one again. And then I end up with this poset. So now the poset is just this relation here, this I curly less than J is corresponding to the, just means that a bead is resting on another bead. So it's touching it and it's well, below. Okay. Sorry, maybe this is not the best way of explaining this, but these pictures are kind of easy for me at least to think about. And okay, so then, so what it's not, so a heap is not just a poset, but it comes with this other information, this labeling function that is remembering which runners a certain bead is on. So that here, that's just each element has the corresponding vertex of the Dynkin diagram associated to it. Okay, so now why did I talk about these fully commutative elements before considering these heaps is because normally if you just pick, as Eva said, even you can pick a non-reduced word and make a heap for it. But in case if the element W is fully commutative and I pick a reduced word for it, then the heap will actually be independent of the choice of that reduced word. So in that case, I can just refer to it as the heap of the Weil group element. So, and we'll be mostly interested in this very, well, I guess, the special class of, fully commutative elements that I already mentioned, the W0 P's of a maximal parabolic associated to a minuscule fundamental weight. So in this case, this Weil group element W0 P is fully commutative, and I can make its heap. And in fact, a little bit, slightly more is true that if I consider this representation V of omega P, then, well, I guess this is almost the definition of a minuscule representation. The weights occurring are in bijection with W mod W of that maximal parabolic. And in this case, all of the minimal length representatives will actually turn out to be fully commutative. And they also have a description that they are exactly those elements that are less than or equal to this W0 P sub P in the left weak order. So what that means is, just to recall, the left weak order is when if I pick V is going to be less than or equal to in the left weak order than W, if some terminal substring of a reduced word for W is a reduced word for V. So as an example, let's go back to the wedge 2 of C4. What we already said that the W0 P in this case is S2, S1, S3, S2. And the poset of Weil group elements less than or equal to in the left weak order than this element is the following picture. And as we can see, all of them are still fully commutative, and they have their associated heaps. Now, one thing that you can notice here is that the associated heaps that show up in the Weil group elements that are less than or equal to this top one, this W0 P, are exactly the order ideals inside this poset of the original heap. So an order ideal is just a downward closed subset of a poset. Okay, so I have these two pictures again matching up the two posets. Okay, so now what we can do is we can use these observations to describe a model for the crystals that for this minuscule representation, where the underlying set is the set of order ideals, or these heaps that we've seen before. And it is commonly denoted as J of the original poset. And the lowering operators have a very easy description in this case. So they are to apply a lowering operator that will be associated to a node of the Dinkin diagram, or equivalently one of the runners in my heap. Just try to remove a bead from that runner. And if that bead is blocked by another bead that's above it, then we cannot remove it. It's kind of stuck there. So then we'll send that heap to 0. And if we can remove it, then we just remove. So as an example, so here I have the F2 lowering operator. I should be removing a bead from the second runner. And fortunately, there is one just here that's available for me to remove. So I can remove it, and I end up with this heap. But I couldn't, for example, remove something from the first runner. So the F1 lowering operator is going to send this heap to 0 because, well, this bead on the top is blocking the bead on the first runner. Is that okay so far? So I just included the crystal of B omega 2 using Young tableau just to, for comparison, I guess, to convince people that this is indeed a model for the crystal. Okay. All right. So so far this hasn't been that impressive, I guess, because we have only really considered these minuscule representations, which are representation theoretically at least pretty simple. So, and we described the lowering operators, and they were kind of easy, but not, I mean, they're sort of easy anyway in terms of Young tableau, because I will never have to decide on which one I'll have to turn into a 2, for example, if I'm applying one of these lowering operators, the F1s. But so the first actual theorem that we have is that if I pick a minuscule fundamental weight and I consider the set of k-fold tensor products of order ideals in my heap, so each of my factors is going to be one of these order ideals, one of these guys here on the right, then the following subset, those k-fold tensor products where phi I is contained in phi I plus 1 as an order ideal, there's a ordering between them, which is by containment. Then exactly this subset with the lowering operators defined using the tensor product rule is a model for the crystal of B k times omega p. So the crystal B of k times omega p will, of course, line the k-fold tensor product of B of omega p with itself. And this is I think, a quite nice description of how exactly this crystal with the high weight k omega p lies inside that big reducible tensor product. Okay. So I know there is a lot of combinatorial notation, but I guess the takeaway here is that we can use these heaps to model crystals of this form, of representations of a single multiple of a minuscule fundamental weight. And I guess one thing that's nice about it is that this is completely type independent, right? I made no reference to the type. I guess I made references to the heap that shows up, but that's somehow a combinatorial object and not related to not necessarily related to the type of the underlying Lie algebra. Okay, so right. Okay, so to describe so I said with the lowering operators defined using the tensor product rule, that's somewhat of a cop-out here because that's usually the difficulty in deciding how to apply these lowering operators, but we actually have a nicer description of these lowering operators here. So first I'll define reverse plane partitions, which are which I want to think of as order reversing maps from a poset to the totally ordered set, this time with a standard ordering. It's called the reverse plane partition of shape of that poset. So a reverse plane partition of shape h of w for this particular w that we've been looking at looks like this. It's the same shape as the beads on that heap. So what I guess this is well, I don't know, maybe it's not worthy to call this a theorem. It's not a very difficult result that there's a bijection between these particular elements that I claimed form the crystal B of K omega P and these reverse plane partitions. So remember, elements that are in this set look like this. They are tensor products of these heaps of this shape, and I can convert them to a reverse plane partition by just counting the number of beads that appear in a certain position. And so, for example, from this, I get, well, I have 3 beads in the lower position, 2 beads on this right side position, and 1 bead in the other 2 positions. And, well, you might argue that sure, that's a map, but how is this map a bijection? But it turns out that you can always uniquely recover one of these increasing sequences of heaps from the reverse plane partition. There's just going to be exactly one that fits the that could have this reverse plane partition. Okay, so this is just a more compact way. So essentially, what this bijection says is that this is a more compact way of keeping track of these k-fold tensor products of heaps, which are otherwise kind of difficult to draw. Okay, and the lowering operators have a nice description in terms of these reverse plane partitions. Is that each lowering operator, fi, will, remember, those should act by removing a bead from one of these k heaps from runner I, and I have to decide on from which one actually. So I want to, in the case of, well, F1 or F3, I don't really have a choice. I'm just going to have to remove the one that doesn't violate this condition that my sequence of heaps is increasing. But in the case of F2, when I have to remove a bead from the second runner, I could remove it either from one of those guys that have it on the top or one of those guys that have it on the bottom. And how do I decide how I do that is according to this formula. So the formula is itself at this point not very important. It's just the point is that the formula is kind of a nice and easy formula in terms of the entries of the RPP. Okay, so let's recap a little bit. So what we did is we constructed a model for the crystals of this form, Bk omega p, where omega p is a minuscule fundamental weight, using these k-fold tensor products or k-tuples of heaps, or to keep track of them, reverse plane partitions of the shape of the original heap that we had. And at least in type A3, but also in general, the lowering operators have a kind of easy and nice description in terms of these RPPs. So what I want to do now is maybe shift gears a bit. So maybe I should stop here and see if there are questions.
Sorry, so do you expect it to be true outside of type A3 as well? With RPP?
Yeah, so this is completely type independent. So everything I said so far works as long as this omega p is a minuscule weight, minuscule fundamental weight. So, and none of the, so that's kind of the, at least for me, the appeal of this project is that this construction is totally type independent, which is usually not the case for crystals. Like we have lots of models for crystals, but you know, they tend to be kind of ad hoc. So here, I guess the trade-off is that I can't do an arbitrary lambda. I can do things of this form.
How about the missing Kirillov-Reshetikhin and crystal operation?
So how to describe that? Yeah, so that's a good question. I mean, yeah, I don't currently know how to think of that nicely in terms of the heaps. Yeah, so what Alan was saying is these are those representations that could be enhanced into a representation of the loop group. So that's what's called a Kirillov-Reshetikhin module. And I guess that's not, so, right, so that maybe that's not completely true, but it's true that if I pick a minuscule fundamental weight, at least I guess in the simply laced case, if I pick a minuscule fundamental weight, then that can be enhanced to a representation of the loop group. and that also has a crystal that's called a Kirillov-Reshetikhin crystal. And I don't know currently how to describe nicely the operation that would give me the action of the affine root, the lowering operator associated with the affine root. But it's a good question. Okay. Right. Okay, so now we talked about heaps and crystals so far. And so we're, as the third thing in the title, we will talk about preprojective algebra modules. So let's consider the Dinkin diagram of G and make it into a quiver by just orienting the edges in some way. And then just to make sure that we don't depend on this orientation, let's double the edges with the opposite orientation. And then we have this doubled quiver, usually denoted as Q bar. And we want to consider the path algebra of this doubled quiver. And we have, and we want to define an element rho that is like this, but the way to think about this is that, and then the preprojective algebra is going to be the path algebra modded out by the ideal generated by this element. And what this means is that at every vertex, I guess, so maybe if I chose my, okay, up to a sign, if I leave and take one step outside of every vertex and then come back using the doubled arrows, that sum should be zero. That sum of linear maps should be zero. That all of those linear maps are going to be an endomorphism at that vertex, and that sum should be zero. So this algebra is called the preprojective algebra of the quiver. Okay, and so what we'll do now is, right, so I guess up to this point, it's not entirely clear why I wanted to talk about these heaps. I could have just equivalently talked about the, certain elements of the Val group, but what I want to make the case for is that these heaps give you a lot of nice intuition and properties of other objects as well. So given a heap of this form, of one of these maximal parabolics that are associated to a minuscule fundamental weight, I can let's replace each element of the heap, so each of the beads, by a single one-dimensional complex vector space, and each covering relation. So each time I have two beads touching each other, I want a map from the higher one to the lower one. That's the identity map. And now what I'm going to do is I'm going to use the labeling function on the heap to define an I-graded vector space where I is the, did I say what I was? I is the vertex set of the Dinkin diagram. And so what I want to do is I want to take a direct sum of those one-dimensional vector spaces that lie above a single vertex, or equivalently, each of those vector spaces that correspond to a bead that's on a given runner. And I'm also going to take a direct sum of those of these identity maps. And this way I obtain an I-graded vector space with maps from, well, I get a quiver representation for this doubled quiver. And I guess this is also a theorem that in this case, the resulting quiver representation is a module for the preprojective algebra. So the preprojective relation is satisfied by this construction, by the module that's constructed according to these rules, and is actually, in this case, if I take one of my elements to be this W0 P, then this is actually going to result in the projective cover of the simple representation, the simple one-dimensional representation supported at vertex P. So let's go to this next picture and look at the what this looks like for our running example. So if I consider my heap of H S2, S1, S3, S2 for A3, I replace each of my beads with a one-dimensional space, and each of these arrows is the identity map. And we see that this is indeed a projective lambda Q module. So how do you check the preprojective relation? I need to check if from the second vertex, if I go to the third one and then come back, is the same as going to the first one and then coming back. Okay. So, right. Okay. So this is a bit of a digression, but I have been kind of focusing on just these particular elements, but as opposed to just general. So I introduced this notion of full fully commutative elements, but then mostly focused on these W0 Ps. So we can basically repeat everything up to this point with fully commutative elements. But for the next steps, I'll need W to be satisfy a slightly stronger assumption than fully commutative. That's the technical term for that is dominant minuscule, which has a definition that's here, but that's not going to be super important for us. But what I want to, as a takeaway, is that this is, this is stronger than being fully commutative. So in the case of I could repeat the entire construction with another Val group element that satisfies this assumption. This dominant minuscule implies fully commutative, so I can still make the heap of the element, and it doesn't depend on the reduced word I choose. And then this set of reverse plane partitions or K tuples of heaps of that shape will serve as the underlying set of the De Mazur crystal, in this case, BW of lambda, where this lambda is part of the definition of being dominant minuscule, or I guess it's implied by the definition of dominant minusculity. But for simplicity, we'll continue working with the these minimal length representatives of W0, because in that case, it's not a De Mazur crystal, but an honest crystal for the entire group, the representation that we have. Okay, so now why is that? So why is all this construction of this lambda module, of the preprojective algebra module from the heap? What extra information does it give us? So there is one piece of this information on the heap, that the beads that are on a given runner are always totally ordered. That's kind of visually obvious, but it's also something that one can prove. And this gives us a way to define another a nilpotent endomorphism on this module, which is defined on the basis, which are the beads, as follows. We just send each bead to the bead that's just the next bead just lower than that one on the same runner. So, or if it's the lowest bead on a given runner, then we just send that to 0. So this is clearly a nilpotent endomorphism of this. Well, I guess it's not clear that it preserves the lambda module structure, but that's also true. So in the picture that we've been looking at, the heap of S2, S1, S3, S2, this operator T, that we'll refer to it as its nilpotent endomorphism T, sends this copy of C to this copy of C, and everything else is sent to 0. So I have this nilpotent operator on C2 that has some, in that case, it will have some Jordan type. Okay, now what I want to think about, so far this is all about L of omega P, and what I want is I want to have a description of crystals with high weight K times omega P. So if I consider the space of submodules of this module, I just take the direct sum of this module that I constructed from the heap K times, and I just consider the space of all lambda submodules. Then one thing that's kind of easy to see is that it has connected components that are indexed by the possible dimension vectors of the module. So those are certainly some disconnected pieces. But what we can do is we can use this nilpotent endomorphism T and extend it to a nilpotent endomorphism of this big direct sum, and I'll still continue denoting it by T. And what we can do is we can obtain a finer decomposition of this space by considering the possible Jordan types of T restricted to each of the vector spaces over the vertices of my quiver. So I can restrict T to each vertex, and any module will have, on any module, this T will have some sort of Jordan type, but I actually have conditions between the Jordan types of adjacent vertices. So in fact, what we see is that the Jordan type of T restricted to M will be given by a reverse plane partition, an RPP, of the corresponding shape, with the sum of the entries in the column I adding up to the dimension of the module. So maybe that's also easier understood in an example. Okay, so the example comes after this thing. This is a conjecture, but it's basically a conjecture that we know is true, is except we want to have a proof that we like more than the one that we currently have. So the conjecture says that the irreducible components of this space are, well, the connected components, remember, were indexed by the possible dimension vectors. And the irreducible components we want to claim are indexed by the possible Jordan types that show up, that I already claimed in the previous slide were indexed by the reverse plane partitions of the appropriate shape. Now, as an example, if we want to consider L of 2 omega 2 in type A3, and I want to, and what, let's just take an example of what does a module with dimension vector, what could a module with dimension vector 1, 2, 1 look like? So I have, so we'll write M sub I for the subspace corresponding to the, above the ith node of the Dinkin diagram. So I will choose a one-dimensional subspace. Well, first let's try to choose the subspace over the second vertex. So I need to choose the subspace of C2, direct sum C2, that's stable under this linear map T, that is this picture direct summed twice. So how can I do that? Well, I either contain all of the kernel of T, so that two-dimensional subspace, and then I can choose M1 and M3 as freely as I want. So those will map into the kernel anyway. That's from this picture, I guess from this picture, right? So this lower subspace here is the kernel of the operator restricted to the second vertex. And anything that maps into it from the first and third vertex automatically ends up inside the kernel. So I can choose those two subspaces freely. Or if I don't contain all of the kernel, well, then I have to, I contain some one-dimensional subspace that's not the kernel. I have to then contain the image of that one-dimensional subspace under the endomorphism T, because my module needs to be stable under this map T. And then M1 and M3 will be determined. And this corresponds to the second type of RPP with the same dimension vector 1, 2, 1. Okay, right. So this is just to demonstrate in what sense. So maybe to give some evidence to why the irreducible components of the space should be indexed by the RPPs. So in this case, there's one question that you can ask is that, do I have to contain? Well, do I contain all of the kernel, or do I not contain all of the kernel? Okay. And here's our next conjecture. So the lowering operators are something about crystals that as I said, they are the only rule that you need to remember is this tensor product rule for SL2, but it's still describing the lowering operators. It always involves writing down some sequence of pluses and minuses, doing some cancellations, and then choosing an appropriate entry to change. And that is, I don't know, it's not very satisfying and sometimes difficult to remember. So this conjecture I like this conjecture a lot. So the lowering operator Fi applied to the reverse plane partitions corresponds to just taking a generic submodule with a quotient isomorphic to the simple module Si supported at that vertex. So what does that mean in terms of the so what I like about this result is that it just means just do it generically, and there's no need to count. Well, I guess in some way there will be some need to count dimensions, but at least here the result is just try to pick a codimension 1 subspace over that vertex that still is a submodule. So maybe to demonstrate this, let's consider our usual running example here, that if I pick L of k omega 2 in type A3, that means that I have, well, this is still a conjecture, I guess, but let's assume this for now, that I have an irreducible component that's indexed by this reverse plane partition. So again, this is just indexing just these 4 entries where each, anytime you're, so A is less than or equal to B and less than or equal to C, and D is greater than or equal to B and greater than or equal to C. And let M be a module in the component that's indexed by this reverse plane partition. Now, when does M end up in this module? As we said, in this case, that just means that the dimension of the kernel of T intersecting the vector space over the second vertex is D-dimensional. So I'm using capital letters for the spaces and lowercase letters for the dimensions. And so because the maps from B to C are going to be all B to C to A plus D, so the maps pointing inward from the first and third vertex to the second vertex are going to be injective, I can identify their images, I can identify them with their images inside the space over the second vertex. So visually, the module should look like this, that I have some A-dimensional space that's mapping to over the second vertex that's, well, sorry. So I have, right, I guess maybe, okay. Let me not say anything more here. I would rather not say something wrong. Okay, so what I want to do is pick a submodule of this M that fits into the short exact sequence. Well, I'm looking for this F2 of M, and I want a short exact sequence where this M appears in the middle, and it has a quotient isomorphic to the simple module supported over the second vertex. So I want to somehow lose one dimension from above the second vertex of the Dynkin diagram. So for that, I need to choose an A plus D minus one dimensional subspace. So when is that? And I want to do it as generically as possible, but what is constraining me is that I need to contain the images of B and C, the ones that are pointing in to my space, right? So if, in order to stay a submodule of this quiver representation, I need to keep containing the images of the arrows that are pointing inward. So generically, this subspace will not contain all of D because, well, a generic subspace, generic codimension subspace doesn't contain any subspace in general, unless B plus C is actually equal to D, right? Because I need to contain the images of those incoming arrows, but otherwise I should be doing it as generically as possible. So let's compute how we can find out what the dimension of this space B plus C is inside the vertex over the second vertex. As I said, we are identifying the images of the maps from the first and the third vertex into the second one by with their images. So what I claim is that the dimension of B plus C is given by this formula. So to get these upper bounds, we use the rank nullity theorem for two operators. One of them is the identity map, and the other one is this operator T restricted to the M2, the space supported over the second vertex. So we get one bound by just writing out the formula for the dimension of the sum of a subspace, and then using the lower bound that I know that B and C both contain an A-dimensional subspace that is given to me by essentially this picture. And to see that the dimension is less than or equal to D, I can apply the rank nullity theorem for the operator T, and I see that the dimension of B plus C should be the dimension of T applied to B plus C plus the dimension of B plus C intersecting the kernel of T. And I get these two bounds, and we claim that this is, well, these are the only two bounds that are relevant for the subspace. And we see that if I'm going to be a generic subspace that's bound above by these two numbers, then the dimension is going to be the minimum of those two numbers. So I know this example is kind of small, so maybe you don't see the full structure, but in general, what you would get is if you have more entries in the RPP in a certain column, or if your heap contains multiple beads over the same runner, then you will get one of these bounds from applying the rank nullity theorem to each of these operators, T0 up to Tm-1, where m is the number of beats on the corresponding runner. And what this leads us to, what is our conclusion here is that B plus C is going to be equal to D if and only if this dimension, if and only if the minimum is the D, that is B plus C minus A is greater or equal to D, or if we slightly rearrange this, then we get this inequality. And now what we can do is we can go back and compare this to what we got by computing the rule that we got from considering these tensor products of heaps, and we see that it is indeed the same rule. Okay, so now I'll need to go back to here. So we see that we here can confirm that a generic subspace that contains that a generic lambda submodule will contain all of the kernel if and only if containing, for that condition to contain the kernel is the same as the condition we get on the corresponding reverse plane partition when we will be decreasing the entry A in there according to the lowering operator. Oh, sorry, I said that terribly. So what we have is we have essentially now two versions of these lowering operators. One of them is given by the rule that we computed using the heaps and the tensor product rule, and one of them that is the that we get from taking this generic subspace, generic submodule. And what we confirmed in this example is that these two agree. And in general, to compute this lowering operator, then we need to know what's the sub among these subspaces of fi of mi intersecting the kernel of t to the j, what's the largest j such that this one must be contained in a generic submodule. And so we are looking for this j because, well, yeah, we want to lose one dimension from this subspace, and we want to do it as generically as possible. So we kind of want to lose that dimension as soon as possible, but we are constrained by having to contain images of certain subspaces. And each of these subspaces, each of these dimensions gives me, each of these bounds is obtained by applying rank nullity theorem to one of the powers of this nilpotent operator that we applied to, that we constructed from the heap. And then, yeah, so this fi of m will contain the kernel of mi intersecting t to j, but not the next power. So that tells us what should be the Jordan type of t restricted to this fi of m. And remember, that should be telling me of which component of this space of submodules should I be going to. So, and of course, the claim is that this is the same as as having the crystal lowering operator rule that we computed on using the heaps. So, right. So I guess this is what I had. I'm not sure how we're doing. Okay, so I'm a bit early, but that's never a problem. Okay, so any questions? Sorry, it's still a work in progress. So I'm not entirely sure about the best way of presenting this yet, but I really like this result that we have. So, you know, there are geometric versions of these crystals due to Kashiwara and Saito, but that construction I always found a little bit more difficult to understand, whereas this one is just essentially doing linear algebra. So I have these nilpotent operators that I construct in this very natural way from the heap. That is, I guess it's hard to motivate these operators in some other way. So that's why I like this connection to the heaps, that this idea that you should go to the next beat on the runner is like natural on the level of heaps, but it's kind of hard to see if you're just thinking of the preprojective algebra modules. And then this flavor of applying the rank nullity theorem to obtain the bounds and then looking for the last time that this minimum is attained is, well, that does have this flavor of the crystal lowering operators, but it's also happens to be the same thing as just doing it as generically as we can. So it's something that you can state very easily. Yeah, sorry. Okay, so any questions?
I think instead of deciding what the Jordan type of T on the entire thing is, could you do that at each vertex in your heap? Say, like, take the stuff below that vertex and say, what is the what's the Jordan type on there?
So in some sense, I think that's probably equivalent, right? That you can. So you would still need to know, I think, well, if you don't check all the way to the top, then you don't know if you have to contain a larger subspace necessarily. So I'm not sure. Maybe I don't understand your question.
Oh, I was just trying to. I'm trying to connect to Robinson-Shenstedt growth diagrams
Mm-hmm.
that would show up in the rectangular case, like like you're doing in these W naught P's in type A.
Mm-hmm.
Like you could be defining naturally for these minuscule heaps in general.
Right. So you're saying that we could look at just the Jordan type below a certain level in my heap?
Not below a certain level, but below a certain vertex.
Below a certain vertex. Okay.
Yeah. So if your whole heap in that original case, or maybe we'll take one of your dominant minuscule cases.
Mm-hmm.
So so I think then the heap is something like a skew partition instead of a rectangle.
Sure.
And but so below any vertex, it's now a skew partition that has a top point.
Mm-hmm.
So it's just a partition.
Yeah.
And inside that partition, I could say, what's the Jordan type of T on that partition?
Yeah.
And so every vertex gets labeled with the partition, and I can ask, for nearby vertices, how are they connected? And get some theory like growth diagrams.
Okay. Yeah. Oh, I guess. Yeah. Sure. So I guess it contains the same amount of information. That's what you're saying, as the whole
more locally described. More locally.
I see. Okay.
Yeah.
Mm-hmm.
So if it's the same, then that's going to be like the Robinson-Shenstedt
mm-hmm.
correspondence.
Right.
It's the same amount of information.